Okay, let's understand the Java float data type. So float data type is a single precision 32-bit IEEE 754 floating value. It means the floating point value will follow a set of procedures to be placed in the registry. Again, the registry is going to accept the binary representation. So in simple words, the floating point number will be converted to a binary number or the binary representation, but it has to go through a lot of procedures, right? The procedures or the standards that is followed for IEEE 754 floating value. Okay. To understand this, I'm going to take a small example. Let us take the number as, so in our case we will take the number as 263.3. So 263.3, right? So this number is a floating point number which has the whole number part as well as the fractional part, right? So the step 1 says try to find the equivalent binary number for the whole number part as well as for the fractional part, right? So let us do that. So 263, let us find the equivalent binary number for 263, right? So 2 ones, 2 2 threes, 2 ones, and the remainder is going to be 1. Again 2, we will have to keep dividing it by 2. We know this procedure already. 65 divided by 2, 3, and 2, remainder is 1. Keep dividing it by 2. Here it is going to be what? 32, 16. Remainder is going to be 0. Keep dividing it by 2. 8 times 0. Keep dividing it by 2. 4 times 0. 2. 2 times 0. And at last 2 ones 2. The remainder is going to be 0. So we will be collecting all the reminders from the bottom to top in this order, right? So 263, for 263 the equivalent binary number is 1 0 0 0 0 1 1 1 base 2, right? So we will have to do the same thing for the the fractional part, right? To convert the fractional part to the equivalent binary number, we need to follow a different approach, right? So the approach is, we need to do the conversion. This has to be converted to the equivalent binary number. For this, will be following a different approach. So the approach is 0.3. We keep multiplying it by 2. 0.3 into 2, right? Which is going to give us what? 0.6. And we extract this number, right? 0. So the resultant value needs to be multiplied by 2 again, right? We get what? 1.2, right? This part needs to be extracted. All the whole number part needs to be extracted, right? This time the resultant value is 1.2, but we don't take 1.2. Instead of 1 by 2, we take what? We ignore the whole number part. We take 0.2. So symbolically 0.2 is what? 0.2. Again it is going to be what? 0.4. And the whole number part is what? We need to extract the whole number part, which is 0, right? Now again 0.4 into 2, it is going to give us 0.8. The whole number part is what? 0, needs to be extracted. Again 0.8 into 2 is going to give us 1.6. Extract this 1, right? Now 0.6 into 2 right? It will give us 1.2, and we need to extract 1, right? And if I keep doing this, if you look at this particular line, this line is similar to, this line. This is similar to this line, right? So the loop is getting created. This is the pattern, right? Even if I try to repeat this, even if I make the consecutive calculations by multiplying it by 2, I'm going to get the same number, 0 0 1 1, right? 0 0 1 1, right? And again, and again it is going to get repeated, 0 0 1 1, and it keeps going like that, isn't it? So, if I write the binary values over here, this time we will be writing it from top to bottom, right? So 0 1 0 0, right? 1 1 0 0, right? 1 1 0 0, right? And it keeps going, 1 1 0 0, 1 1 0 0, and it will keep going just like that. So the step 1 has been achieved, right? We have found the equivalent binary number for the whole number part, and we have got to know the equivalent binary number for the fractional number part, right? Now we have to do this step 2. So let us write this number down, 150 150 this is for the whole number part, and for the fractional part 0 1 0 0 1 1 0 0 1 1 0 0, right? 0 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0, right? And it keeps going like that, right? Now next thing is step 2. The step 2 says this number needs to be get converted to the scientific notation, right? Because scientific notation, understanding the scientific notation is really simple. If any large number or if any small number, those numbers needs to be represented in a simple way, in a simple readable way. We use scientific notation. For example, if let us say that I have a number like 127 6 829.2763. For an example, if I have this number, if I need to convert this into the equivalent scientific notation, right, I need to shift this decimal point towards its left, right? And I have to ensure that the resultant number is going to have only one whole number part, which means I need to shift this decimal point to here, right? How many places it needs to be shifted? 1 2 3 4 5 6 places, right? Now I can represent this like 1.2 768292763 into 10 to the power of 6. Here the 6 is representing the number of places that the point has gone through to be shifted. So in this case 6 places, 1 2 3 4 5 6. So I can do the same approach. I can follow the same approach to convert the binary number to the scientific notation, right? In our example, I have a point here, right? This point needs to be shifted to here, right? So how many shifting does it require? 1, 2, 3, 4, 5, 6, 7, 8. 8 shifting. So I can rewrite it like 1. I'm just copying the same numbers, only the decimal point is shifted to 8 positions, right? So because it has been shifted to 8 position, I need to multiply it by 2 to the power of 8. Why 2 to the power of 8? Because this is a binary number. Binary number, the base of the binary number is 2, right? So we have completed the second step. And the third step is the last and final step. We need to convert this number to, we need to write this number in IEEE 754 format. Last step, we need to convert this number to IEEE 754 format. How do we do that? So the IEEE 754 format suggests that, okay, see, since it is a 32-bit number, bit number, right? The first bit is reserved for the signature, and the remaining 8 bits, the next 8 bits, is reserved for the exponent value. This first bit is reserved for the signature sign, right? This is called as MSB, most significant bit, which is always reserved for the signature. If it is a negative number, like you use 1. If it is a positive number, you use 0. You replace with 0. And the remaining 23 bits, right? And if you count it, the remaining 23 bits, right? We call it as mantissa, and it is reserved for fractional values, right? So the number that we have taken for our example is 263. 263 is a positive number. So positive number can be represented with the bit 0, bit value 0. This part is completed. And exponent value, in our case, the value of the exponent is what? 2 to the power of 8. 2 to the power of 8, right? So 2 to the power of 8 in the sense, right? So whenever you're trying to consider the exponent part, we should also consider the bias. We need to take care of bias, right? So the bias says that, right? So exponent can be a negative number, it can be a positive number. In our case, the exponent value is what? The positive number. So the bias value is 127. For 8 bits, it's 127 because 8 bits is going to have 1 bit reserved for the signature, right? So when you represent the remaining 7 bits, it is going to be 127, right? So if it is a positive number, if the exponent is a positive number, add this with 8, add this with the number 127 plus 8. If it is a negative number, subtract this. Since it is a positive number, we are going to get what? 135. Find the equivalent binary representation for 135, and you get what? Like by following this approach. If you find the binary equivalent for 135, we will be getting 1 0 0 1 1, right? This is for okay. This is how the 135 can be represented. 1 0 0 0 1 1, right? So this exponent value is going to have 1 0 0 0 0 triple 1, right? The next one is mantissa, the fractional part. So you add all this in the mantissa. In our case, start from here, 0 0 0 0 0. We have three ones, 1 1 1 0 1 0 0 1 1 0 0 1 1 0 0, and it goes, right? Now divide, consider only the 32 values, because this is a 32 bits registry. So the first four values 0 1 0 0, second four. For the better understanding, I am just separating it so that it will be easy for us to observe. Remaining for 1 triple 0, remaining for 0 0 1 1, remaining for 1 0 1 0, remaining for 0 1 1 0, remaining for 0 1 1 0. So 4 8 12 16 20 24 28, and we need to consider 1 1 0 0 0 1 1 0. So this is what the final answer. So this value will be stored in the register. Binary number. This binary number will be stored internally in the register. This is how you can convert the decimal value, what we call it as the floating point number, to the equivalent decimal number. We have followed three approaches and we got this answer. This is the final answer. Right? So that's all about this. We will try to understand the how to do the opposite conversion, right? Converting the binary number to the equivalent decimal value by using IEEE 734 standards in the next class.